Susskind and Nambu were those that, independent of each other, found out that precisely this formula is, funnily enough, the formula for scattering of strings against each other. Strings with some properties given by quantum mechanics and relativity theory, but it is basically strings under these conditions, which are well known to be true in high energy physics, in physics in general. So this was a scattering of strings against strings. But actually, I was working at that time together with my advisor, Zero Koba, who died too young, and we were working on generalizing the Veneziano model to more complicated scatterings, where you scatter two particles against each other and get a lot of particles out, not only two, like the Veneziano case. So we generalized to many more particles, and we wrote some paper about how to formulate that with very elegant mathematical formalism. So we developed the mathematics and the generalization of that. And then, inspired by these things and some ideas about that hadrons are probably composed of a lot of particles that interact very strongly and so on. Then I found to this suggestion, this idea that it should be strings, and then it turned out that this reproduced this type of model, like the Veneziano model, for instance, our own generalization of it.
So is this the smallest part that we know of? How does quarks play into this? Is this yet a smaller part than strings, or how? What is that?
That's good. No, now I have to tell you that in the original development of string theory, when Susskind, Nambu, and myself independently developed this idea of the Veneziano model being a string model, then the whole thing was meant to be a theory for these type of particles called hadrons. At that time, one had ideas that these hadrons were composed of quarks, but one didn't seriously discuss, or not at all discuss, the gluons.
Yeah.
So at that time, one were developing quark ideas, but it was meant that it was these hadrons which are nowadays thought to be built from quarks and gluons, which were the strings. And they are in some sense strings, I think. Yeah. So in a way it was right, but it is not so obvious. And the perfect description of these hadrons as strings has not really appeared. As I was once having a bet with a later director of our institute, that Knud Hansen, that we should before some machine started, one should have a model where one describes the theory in terms of this kind of string theory, and that would work so well that one would basically let the computer use that. This turned out not to be true, as I had expected, and I lost my case of beer. But it has, to some extent, appeared to be true, because now one uses in Lund, it is called, because they were especially doing it there, one uses a kind of string models which are not the perfect strings I had hoped for, but one uses computers compared with that, and now it is also using basically the gluon theory, which was not there. So one does something in that direction today in practice. When one wants to see what comes out of LHC, then one compare with these computer simulations of what should happen. So one run the whole experiment, what happens in these collisions, by the theory and find out. And then one can see what modifications of theory might be needed. But in a way, I think the so far running, I think one of them said, it's surprising how well the theory goes.
Well, that's nice. You've been, I do want to talk a little bit more about random dynamics here, but have you been working on the Casimir effect as well? Is that part of your job, your work?
Worked on what?
Casimir effect, the Casimir effect.
I have been working on Casimir effect. That's right. I have been working something a little bit. I have been working on Casimir effect in a way. I was working together with Norwegian Eva Breivik, where we considered some strings which had different tension in different parts of the string. So it was somehow a tense string and a less tense string connected together, and we calculated also sort of generalized Casimir effect on such strings.
Okay.
That's right. So I have worked on Casimir effect. I have also been discussing Casimir effect with a student of mine, Sven Erik Roux, who had the idea to look for the possibility or for the question, how do we really know that the vacuum is so complicated as a high-energy physicist usually will tell it is? And then, of course, I have to tell you that the vacuum in which we live, in the picture of modern quantum field theories like the Standard Model, is very complicated because it's described by quantum mechanics and it has some fields, and these fields do not even have definite values but are in superpositions of different values. And this concept of superposition is only meaningful in quantum mechanics. So one has this, for quantum mechanics, special feature that particles can be in different places in the same time, and fields can have different values at the same time. And these mysterious quantum mechanics, this is true and realized even in the vacuum, in the empty space. So the empty space is a very complicated structure according to that.
Yes, exactly. And I mean, have you, if we talk a little bit generally about the quantum mechanics or the quantum effect and so forth, many people now are talking about this, the effect of the observer as well, in terms of quantum mechanics, that it seems to, it's a particle in one sense, it's a wave in another, and it seems to be popping up wherever the observer is looking. That's more of a popular way of using the terminology to explain it. But how would you explain the whole quantum mechanics field? It's been kind of coming more and more into the popular arena, if you will, lately. What do you find interesting with it? Is it a mysterium, really, or have you been able to understand it?
I think it is a kind of mystery. I think there are well-known mysteries in quantum mechanics.
Yes.
And it is, of course, perhaps one of the ways of formulating one type of mystery. That is, according to the so-called Copenhagen interpretation, then when you have prepared your state, you can at some point measure a certain variable for the particle you consider.
Yes.
And then, according to this Born's probability rule, you get from the quantum mechanics a way to calculate the probability for getting different values of this result. But once you have measured it, then somehow the particle has the quantity you measured with that value which you measured. And this is rather strange, because it began to have this property which I said that it was in a superposition of having different values, and